Alright everyone, welcome back. We'll go for another video here. Let's look at Coulomb's law. So this is really physics. Unfortunately, we're in that realm where physics and chemistry cross over, so we're going to have to learn a little physics. It's pretty basic though. You probably got most of this in 8th grade. So here's the idea. We have to think about the idea of charge. There are two types of charge. There is a positive charge, and there are negative charges. This was kind of an arbitrary assignment. They're just opposites, and this is the notation we've been using for rubber and noise. So you have positives and negatives. Hopefully some point in your 8th grade experience, you learn that if you put two positives together or two negatives together, they are going to want to repel. They are going to want to move away from each other. If you put a positively charged thing next to a negatively charged thing, they actually want to attract, and they'll pull towards each other. This force that occurs, either the repulsive force or the attractive force here, is known as the electrostatic force. Or better yet, the electromagnetic force. They're basically the same thing, the key difference here being that electrostatic implies not moving. If you have a charge that's not moving, then it creates no magnetic field, so therefore you have no magnetic portion. A charge that is moving creates a magnetic field as it moves, and therefore creates a magnetic force as well as a electrostatic force. So you kind of have both to deal with. So how does this apply to us? Well, you also probably learned at some point that there are parts of an atom. And in the next few videos, we're going to talk about how the parts of an atom came to be. You have neutrons, you have protons, and you have electrons. Neutrons are neutral and carry no charge, so this whole thing doesn't matter to them. Protons are positive, and electrons are negative. Now this is, once again, totally arbitrary denotation. Protons could have been negative, electrons could have been positive. It's just that's the way that the guy that originally figured this out decided to set it up. So what does that mean for us? It means that if I have two electrons that get near each other, those two electrons are going to want to move away. Okay, that's an electron, by the way. We denote that as the E with a little minus sign to show that it's negative. It also means that if I have two protons, they're also going to want to move away from each other. P positive denotes proton. And just in case someone out there is curious, a N with a naught or a 0 at the top of it represents a neutron. No charge, 0. Okay. Now, this pretty much makes, it's not too complicated. The next thing we're going to have to look at is the fact that our charges are moving. And this is going to be really pertinent for the couple of experiments we're going to talk about in the next couple of videos. Let's say I set up an electric field. An electric field can be set up as simple as two metal plates that are connected by a voltage source. That's a voltage source. Oop, I had them off the screen. Voltage source, for those that haven't seen the notation here. And what this does is it's essentially going to cause a large amount of positive charge to build up on this side, and a large amount of negative charge to build up on this side. Now imagine I take a electron. My electron's right there. and I shoot it between these plates. What's going to happen is that electron is going to come in and curve upwards as it travels between the plates. Why? Well, the idea here is that the electron is going to be attracted or pulled towards the positive plate due to the attractive force, the attractive electrostatic force, and is also going to be getting pushed away from or repelled, okay, by the negative plate, which is going to cause it to deflect in that direction. We can mathematically describe this, and I'm not going to go into a crazy derivation here on the video because frankly we just don't need to know it. But if we have, let's say we have two charges in space, let's say we have an electron and a proton, we know that they're going to be attracted towards each other, but with what amount of force? Well, the force applied by the electrostatic is equal to some constant. Don't worry about the constant. It's constant, it doesn't change, times the charge of the first thing times the charge of the second thing, or in this case, the charge of the electron times the charge of the proton, divided by the radius squared. And we use radius, but radius really could be replaced with distance. But we often talk of radius because these are points in space. It's easy to think of this kind of a circle around these things. But distance, radius, both will work. So what ramification does this have for the models that we're going to start discussing? Well, the idea here is, let's say they both have a charge of, let's just say they both, for the state environment, have a charge of 1. So Q electron is 1, Q proton is 1. It doesn't really matter what the charges are, but if we start plugging them into our equation, assuming K is constant, it's going to stay the same regardless. And let's say they're separated by a distance of 1. Okay, I'm leaving units off for a reason here, so our distance is equal to 1 as well. That would make our force equal to 1 times 1 over 1 squared, or 1. Okay. Now let's say I double the distance. So now it's force equals 1 times 1 over 4. So now our force is 1/4. So by doubling the distance, we've reduced it by a factor of 4, the force that is, or the attractiveness here. If we increase that to a 3, the force is going to go to 1/9, the attraction. So as radius increases, the force between the two charges goes down drastically. That's the first key piece. And the second key piece is it goes down faster than if you increase the charge. Or bigger charge is bigger force, greater distance is less force. So what you should do here, I'm not going to do it on my notes, is you should write a little statement here, a description of what we just talked about in terms of what this equation tells us about two charges. And I'm going to go ahead and cut it. I'm going to go ahead and cut the video off there. I'm going to try to make the videos actually a little bit shorter. They're easier to upload that way, and I think they're really easy, a little bit easier to digest when they're. So that's Coulomb's law.